All right, guys, welcome back. So today we are focusing a little bit more on endothermic and exothermic reactions and how do we tell what's happening in them. And I'm going to show you two experiments that I'm going to do in my kitchen so that you guys can follow along with me. But before we begin, we should probably just redefine and make sure that we understand what endothermic and exothermic reactions are. And by the way, I have some notes that are attached to this. So if you would, you can type them up, you can write them up, whatever you want, but they'll help you on later on for your tests and quizzes and things like that. Just an extra little thing that I'm giving you. So if you use it, that's great. If you don't, that's fine too, but it's just to help you. So the first question on there is, what is the difference between endo and exothermic? Oh, it's like shaking the whole iPad when I do that. So it kind of tells you in the title, right? It has to do with what is happening to thermal energy in the reaction. So again, reactions are when we're taking more than one molecule, we're adding them together, and then basically what you're getting out of the reaction is a completely different arrangement of those atoms. So endothermic and exothermic. Now that has to do with what's happening with energy. So in an endothermic reaction, energy is being absorbed by the reaction, okay? So energy, and I'm just going to abbreviate as an E plus, is absorbed, okay? In an exothermic reaction, you're going to have energy released. In other words, it's going to be a product. It's going to be something that you get out of your reaction. So energy is released from the reaction. Okay, and I'm abbreviating reaction there like so. So I'm going to show you two experiments, and you're going to see if you can figure out if they are endothermic and exothermic. If you'd like, you can actually do these. They're fairly easy. You just need some things around the house. So let me pause it for a second. All right, guys, so let's try this first one and see what happens here. So things that I needed here, I have a thermometer, I got some vinegar, I have some baking soda, and I got my jar. So let me start by adding in some vinegar. So I'm going to add in I'm trying to estimate here because I don't have a graduated cylinder, so trying to get about 20 milliliters of vinegar in here. So let's try that, and then I'll add a tiny bit more. Okay, I think that's about right. So notice what vinegar looks like at room temperature. So room temperature, clear. Definitely has a smell to it, right? It's very vinegary. It's very sour, right? Now, let's also get a starting temperature because I'm going to be adding everything into this vial. So, starting temperature here, I have an instant read thermometer that I use for like cooking and things like that. What's it say there? So that is going to be our starting temperature. Let me write it down as a good scientist would. Bam, I got my notebook here. So I'm going to call this 79 degrees Fahrenheit. Now, normally we would want to do this in Celsius, but my little thermometer dude is only going to do Fahrenheit. So starting out fairly warm, warmer than the room around it. I'm going to add in about a teaspoon of baking soda. And when I do that, you'll see the reaction happen pretty much instantly. And we also want to see what's happening to temperature. So I'm going to keep this in here for a second. So it's still about 78.8. So we'll see that jump a little bit. But I want to show you what happens here when I add the baking soda. So, all right, now let's look at the temperature. It's still bubbling. So look at it. It jumped, right? But it's jumping in the opposite direction. So now I'm looking at 71, jump down to 70. Now it's jumping up a little bit, 70.5. And technically we would want to see this out until it kind of stabilizes, which it looks like it might already be starting to do. It went down a little bit to 70.3. So it's going down a little bit. $71. 70. I'll give it a little bit longer. I might cut it and then edit it out and all that good stuff. So it's a little bit easier to follow. So 70.2, Okay, it's probably starting to even out right there. But notice, would we call that an endothermic or an exothermic reaction? Think about that. That's experiment 1. Write down your answer and see if you get it right when I explain it after the second experiment. All right, so now we're going to start experiment number 2. So experiment number 2 would look something like this. I'm going to take hydrogen peroxide, and I'm going to take, let me make sure. Yeah, I'll do about 40. So again, this isn't, I should have, what do you want to call it? A graduated cylinder, but in this case, I don't because I'm at home. So that seems like about right. I'm pretty good at estimating these things. If not, then maybe we'll have a surprise on camera. But here is my hydrogen peroxide. Bam. Cool. Now, what I'm going to do is, like we did before, we want to get a starting temperature. So I wiped off my thermometer, I cleaned it, instant little thermometer here. And keep in mind, this is what it looks like observation-wise, clear. And let's get a temperature. So our starting temperature here is going to be about 72.4, let's say. All right, so what I'm going to do to this is I'm going to keep the thermometer in here because, again, instant reaction. And I'm going to add some yeast. So yeast, which we use for baking and things like that. Keep in mind, so yeast, I actually had to search all over town to try to find because everybody in the world is baking bread right now. So it was actually not a super easy find. So let's add in a teaspoon of yeast here. Yeast is actually a living thing, which is what allows the bread to rise. So let's see what happens. So added in my yeast. Oop. All right, thermometer. Notice what's happening here. And it's very subtle. It isn't as instant or as violent as a reaction as we saw in the last one, but I am starting to see some bubbling down at the bottom here. So notice what's happening to the temperature. And that's what it is looking like. It's pretty gross. But what's happening here, there's a reaction occurring between the yeast and the hydrogen peroxide. So I'll let this go for a little bit longer just so you guys can see it. We would, ideally in a perfect world, we would want to keep taking measurements for about, oh wow, look at that jump. So now we're in the 80s. That's a pretty high jump. So normally we would want to keep this going for like, I don't know, maybe 2 minutes or so, something like that, until, again, it kind of levels off or stabilizes. But right now, this reaction is actually still going fairly strongly. Ooh, now it's jumping. Jump, jump, jump. So now we are at, what are we at now? Still at 84. I got 84. Ooh, is that a 90? I think it depends. So where the two meet is where it's probably going to be the hottest. So I'm probably not holding it the most steady, but notice that the temperature is continuing to climb. It is not lowering, it's increasing. So that's experiment number 2. So you want to try to tell me if that is going to be an endothermic or an exothermic reaction. So if you want to look and see what that looks like. Whoops. Oh no. I just spilled it on my kitchen table. Let me clean that up. Okay, so you just saw those 2 experiments, and we want to figure out which one was going to be endothermic and which one was exothermic. So the experiment number 1 was the one that I did with the vinegar and baking soda. If I were to graph it out, and this was somebody else who did it and used Celsius, so I used this graph. I found it a little bit easier here. So basically, if I were to graph it out, and what we saw actually in the video, you can even go back and check, as I went from all the way down up from 79 degrees Fahrenheit, and it dropped all the way, I think, to like 70-ish or something like that. So the surroundings got colder. So therefore, that would actually be an example of an endothermic reaction. Because what was happening here And this is where some of you guys might get a little bit confused. So it's endothermic because energy is being used to break those bonds. Way back at the beginning of the year, we talked about thermal energy and temperature in the connection there. And there's still that connection there. But instead of speeding molecules up, we're using this energy to break bonds, okay? That is the whole point of what we are doing here. So we're breaking bonds here. Oop, sorry, you can hear my dog here. Let me pause it. Okay, so experiment number 2 was the yeast in hydrogen peroxide. So that one was a little bit of a different change and a little bit more dramatic in terms of temperature change, because we started off at 72.4 degrees Fahrenheit and it rose all the way up to, I think, like, didn't we say 79? No, actually it went into the 80s. It was like 85 or so. So notice on this graph, they show the same thing happening. So energy is going from this level all the way up for experiment 2. And then same here is happening for experiment 1. So experiment 2 would be an example of an exothermic reaction because heat is a byproduct. It's a product. So it's an exothermic. There we go. So exothermic reaction there. Perfect. So now that we have those explanations, let's talk about some other examples here. And these can be found in the notes as well. So a common way that you can show what's happening in a reaction is to use a graph. Now this graph is going to show you basically what is happening in terms of energy in what you put in versus what you get out. So let's start with our endothermic reaction. So in an endothermic reaction, you have reactants that are going to be down here in terms of energy. They're going to be raw materials. And again, reactants are just what you're putting into the equation, what you're putting into the reaction. As the reaction goes on, however, you're going to get something that goes like this. In your products, what you finally get out is going to be much higher in terms of energy. And the reason why is because some energy is being put in. So I'm going to do that in a different color here. But we're basically showing that the difference here, that the reactants are really low in energy versus the products which are really high in energy. And that would be an endothermic reaction. So green arrow means energy absorbed. Okay. Now let's look at our exothermic reaction. So in an exothermic reaction, you're going to have the opposite. It's going to look like a downward hill. So you have your reactants at the top. They're going to be really high in energy. And then as the reaction goes on, you're going to see something like this where it's going to go down. And you have your products being lower in energy. Now here, where does energy go? Energy gets released to the environment from those reactants. Okay. So that's what I mean when it has that space to draw what those graphs mean. I will ask you to basically be able to recognize what's going on in these graphs. They're not super hard. They're just, there's only 2, and you can kind of just tell if you read your axes. So chemical energy is on the y-axis, and the direction of the reaction, it's just showing as it goes on, it's changing. So finally, we have this last section here where we're going to talk about some specific examples, and I want you to try this on your own. So if you want to pause the video and see how many you can get right, that would be good practice. If not, don't worry. I'm going to talk through them, so don't worry about it too much. We're not going to have a test immediately or anything on this, but you'll have your Google form quiz on Friday. So let's go ahead and go through these. Hopefully that gave you enough time to pause it if you needed to. So let's go through, and I'm just going to write EX or EN for this. So for the first one, if the surroundings get hot, energy is getting released. So that is exothermic. If the energy diagram, what I just drew, is going downhill, then it's going to be exothermic as well, because you're going from high energy to low energy. If energy is a product, guess what? We got EX, right? It's a product. It is exothermic. If the reactants end up having more energy, again, bam, we got exothermic. If the products have more energy, if we're going uphill, I misunderstood uphill and downhill. That should be, if we're going uphill, it's going up. So this should be EN. I'm sorry. It's late. I am having troubles. If the products are having more energy, if you're climbing to them, that should be endothermic. If the energy diagram is downhill, that is going to be exothermic. Surroundings get cold. So that was what we just saw in our experiment. That is an endothermic reaction because it's getting absorbed by the molecules and the surroundings are getting colder. If energy is a reactant, that would be an endothermic reaction. Now these are some more examples. So rusting iron, number 9, the chemical formula for iron rusting looks like this. You have solid iron plus oxygen in the presence of oxygen yields rust. In the actual chemical name for rust is ferrous oxide, and it looks something like that. So what am I doing here? I'm going from raw materials to a more complex one. I'm building something that is more complex and rearranging these. So that is going to be an endothermic reaction. Okay. Baking bread, again, endothermic reaction. Combustion, any kind of combustion is always going to be exothermic. Photosynthesis. So photosynthesis, you're going from these raw materials of water. Here, I'll actually draw that chemical formula down here too. So photosynthesis looks like this. You're taking water, you're taking carbon dioxide, and you're taking light energy. Remember, light is energy as well. And you're getting out glucose. You're getting out this molecule right here. And you're also getting out some oxygen. So we would call that an endothermic reaction as well. Hand warmers. So hand warmers are going to be an exothermic reaction because basically you're warming up the hand. So from the hand warmers, the heat is leaving the system and going to the surroundings. If you're breaking hydrocarbons, this is just a type of molecule. So you're just breaking it apart. That would definitely be exothermic. Same thing going for your self-heating cans. So they're keeping the surrounding liquid, they're keeping that warm. So that's going to be exothermic. It's a product of the whole reaction. Again, breaking down, that's a key word here, decomposition, breaking down, that's going to be endothermic. Glow sticks. Glow sticks are kind of interesting. So glow sticks are going to be exothermic because they're giving off energy in the terms of light. Because what glow sticks are made of, they're made of some dye, they're made of usually some hydrogen peroxide and some other things. When you break that little thing of liquid in the middle, you're causing all those things to mix together. And when that happens, electrons change energy levels, which gives off that glowing light. Okay. So number 18, an ice cube melts. So think about what's happening with these changes in energy. So with an ice cube melting, you're going from a solid to a liquid, right? So if you are going from a solid to a liquid, then you would be actually, what was I going to say? That would actually be in... Whoops, where am I? That would be an exothermic reaction. Cooking an egg in a frying pan, that is going to be endothermic. We talked about cooking and all of that. Burning a match, again, burning, that's going to be exo. Morning dew on grass and plants, that is going to be, let's see what I have here. I have exothermic here. Let's see. You know what? I don't really like that one. Scratch this whole question because there's multiple ways that you could think about that one. Okay. Puddle of water evaporating. That one is going to be endothermic. Nuclear fission. You create a lot of heat. That's the reason why we use it as an energy source, use nuclear. And then we're going to scratch 24 as well because we're not really getting into the definition of system yet. So don't worry about those ones. All right. All right, guys. So that is it for today. I will see you tomorrow. And don't forget to fill out the Google form just to make sure that you're paying attention. All right. Bye, guys.